Earthquakes, the very mention of the word can send shivers down our spines. The very word conjures images of destruction, fear and chaos, buildings reduced to rubble, streets filled with debris, and lives turned upside down in an instant. These natural phenomena, often unexpected and always powerful, have shaped our planet and human history for millennia. From ancient times to the modern era, earthquakes have left their mark. But what exactly causes the ground to tremble beneath our feet? What forces are at play deep within the Earth? Understanding the forces at play deep within the Earth is crucial. It involves studying the layers of our planet and the movements that occur far below the surface. These seismic events are not random occurrences. They follow patterns and are influenced by the Earth's internal dynamics. They are the result of the dynamic and ever-shifting nature of the Earth's crust. The constant movement and interaction of tectonic plates creates stress and tension. By delving into the science behind earthquakes, we can better prepare for their potential impact and mitigate the risks they pose. This knowledge helps in designing safer buildings and planning effective emergency responses. The Earth's crust is broken into numerous fragments known as tectonic plates. These plates are like pieces of a giant jigsaw puzzle. These plates are in constant motion, driven by the heat emanating from the Earth's core. The intense heat causes the mantle to flow, pushing the plates in different directions. The interactions between these massive pieces of the Earth's puzzle are what give rise to earthquakes. When plates collide, pull apart, or slide past each other, the energy released can cause the ground to shake violently. To understand earthquakes, we must first journey to the Earth's interior, where the story of tectonic plates begins. Beneath the surface lies a hot and dynamic layer called the mantle, which plays a crucial role in the movement of the Earth's crust. The mantle's heat creates convection currents that drive the movement of tectonic plates, much like a conveyor belt in constant motion. These plates, which make up the Earth's lithosphere, are constantly shifting, drifting slowly but powerfully over the mantle. Imagine a pot of boiling water. The heat source at the bottom creates currents, causing it to rise and fall, similar to the convection currents in the mantle. Similarly, the heat within the Earth's mantle creates convection currents that push and pull on the tectonic plates above, driving their movement. The boundaries between these moving plates are where the action happens, where the Earth's crust is most dynamic and active. As plates grind against each other, immense pressure builds up over time, creating tension that can be released suddenly. This pressure eventually exceeds the strength of the rocks, resulting in a sudden release of energy in the form of seismic waves, which we experience as earthquakes, shaking the ground and sometimes causing significant damage. The Earth's tectonic plates interact in a variety of ways, each with its own unique seismic consequences. There are three main types of plate boundaries: divergent, convergent, and transform boundaries. Divergent boundaries are regions where tectonic plates move apart, allowing magma to rise and create new crustal material. Earthquakes at divergent boundaries tend to be less intense. Convergent boundaries are zones of intense geological activity where tectonic plates collide, resulting in subduction or uplift. The Ring of Fire is a prime example of convergent plate boundaries in action. Transform boundaries occur where tectonic plates slide horizontally past each other, like the San Andreas Fault in California. Each type of plate boundary presents its own unique seismic hazards, crucial for assessing earthquake risks and implementing mitigation strategies. Beyond tectonics, other factors can also trigger earthquakes. Volcanic activity can generate earthquakes as magma rises through the Earth's crust. Human activities, such as the extraction of oil, gas, and groundwater, can alter stress distribution within the Earth's crust. The construction of large dams and reservoirs can increase the weight on underlying faults. Other natural phenomena, such as landslides, meteorite impacts, and glacial movements, can also generate minor earthquakes. While these events are less common, they highlight the dynamic nature of our planet. When an earthquake strikes, scientists use various scales to measure its power and impact. These measurements are crucial for understanding the earthquake's potential damage and for preparing appropriate responses. The most well-known scale is the Richter scale, which quantifies the magnitude of an earthquake. Developed in 1935 by Charles F. Richter, this scale has been fundamental in seismology. The Richter scale is logarithmic, meaning each whole number increase represents a tenfold increase in wave amplitude. This exponential growth helps scientists understand the energy released by the earthquake. For very large earthquakes, scientists use the moment magnitude scale, which is based on the total energy released. This scale provides a more comprehensive understanding of the earthquake's true size. The moment magnitude scale provides a more accurate measure of the size of large earthquakes. It has become the standard for measuring significant seismic events. In addition to magnitude, scientists assess the intensity of an earthquake, which measures its effects on people, structures, and the environment. This helps in evaluating the earthquake's impact on different areas. The modified Mercalli intensity scale assigns Roman numerals to describe the observed effects of an earthquake. This scale ranges from I, which is barely felt, to Uwatit, which causes total destruction. Understanding the difference between magnitude and intensity is crucial for interpreting earthquake data and communicating risks to the public. This knowledge helps in disaster preparedness and mitigation efforts. The effects of earthquakes can be devastating, ranging from ground shaking and surface rupture to tsunamis, landslides, and liquefaction. Ground shaking is caused by the passage of seismic waves through the Earth's crust. Surface rupture occurs when the fault responsible for an earthquake breaks through to the surface. Tsunamis, giant sea waves triggered by earthquakes, can travel thousands of kilometers across oceans. Landslides occur when slopes become unstable due to ground shaking. Liquefaction causes saturated soil to lose its strength and behave like a liquid. The impacts of earthquakes extend beyond immediate physical damage. They can disrupt essential services, leading to widespread economic losses and social disruption. Certain regions of the world are more prone to earthquakes due to their location along active tectonic plate boundaries. The Circum-Pacific Belt, also known as the Ring of Fire, is a zone of intense seismic and volcanic activity. This region accounts for approximately 90% of the world's earthquakes. The Alpine Himalayan belt marks the collision of the Eurasian, African, and Indian tectonic plates. The Mid-Atlantic Ridge, a divergent plate boundary, is also seismically active. Understanding the location of these earthquake-prone zones is crucial for risk assessment and disaster preparedness.